Welcome to an ultimate review on confidence intervals to help you get a 5 on the AP Stats exam. All right, I want this to be a quick video, maybe not that quick, but quick in terms of confidence intervals is a pretty big topic. I'm going to try to hammer everything I can that actually pertains to what might be on the AP test this year. That way you could get a really good score. So please don't forget to hit that like button. I really appreciate it. Let's dive right into it. So the general idea of a confidence interval is this. We want to estimate the value of a population parameter, so we start with the sample statistic, which we call the point estimate. We then add and subtract a margin of error to that sample statistic to create an interval that we have a certain level of confidence the true population parameter is in. So again, the only way we can know a population parameter is if we do a census. We don't got time for that, especially with really big populations. So we do the next best thing is we take a sample, and from that sample we get a statistic, and we start with that statistic as our point estimate. We go up a little bit, we go down a little bit to create a confidence interval that we're confident the true population parameter falls within. Now, in this course, for the most part, there are 5 different population parameters that we could look for. We could look for a population proportion, maybe the proportion of all kids that vape across the United States. We could look at the difference between 2 population proportions. So maybe we're going to look at the difference in the proportion of kids in Ohio that vape versus the proportion of kids in California that vape. We could also look at a population mean. Maybe we want to find out the true mean weight of all bullfrogs. We don't know what it is. We could also look at the difference between 2 population means. So maybe here we're going to look at the difference between the mean height of female police officers and the mean height of male police officers. Lastly, we could look at the slope between 2 quantitative variables. So we might get a scatter plot that shows us the slope in a sample between 2 quantitative variables, but we might want to say, well, what could be the true slope between those 2 variables amongst the populations? We could also do a confidence interval for the slope. So these are the 5 different things that we could create a confidence interval to try to figure out. Now, there is a very generic form for a confidence interval that is given to you on the AP Stats formula sheet. Here it is. It's actually a pretty nice, simple formula. All confidence intervals look like this. They start off with a sample statistic. Again, this is a value that comes from your sample. Could be the proportion from a sample, could be the mean of a sample, could be the slope from a sample. Then we go up and we go down, that's that little plus or minus right here, by what we call the margin of error. Now the margin of error is this entire back part that is actually made up of 2 values multiplied together. And I have a typo there, 2 values multiplied together. So the first is the critical value. The critical value is determined by the given level of confidence. So if you want to be 95% confidence or 98% confidence or 99% confidence, that critical value is going to change. And then the second thing is the standard error of the statistic. Now this is actually the same formula as the standard deviation of the sampling distribution, but we're using the sample statistics instead of the population parameters. So hopefully you know a little bit about sampling distributions, and you know that there's a couple different formulas for the standard deviation within a sampling distribution, and the different formulas all depend on what your sampling distribution is showing. But if, sampling distributions are based on the true population parameters, and if we don't know those, we have to use our statistics in those same formulas, and that's where we get the standard error. Let's talk a little bit more about each of those values. So the critical value, this is how many standard errors. I wish it could be standard deviations, but again, standard error is like the twin brother standard deviation that we're willing to reach up and down in each direction to be confident our interval will contain the population proportion or the population parameter. A proportion is just an example of that. Now, a critical value commonly is known as a Z-star or a T-star. Now, we use Z-star when we're working with proportions. We use T-star when we're working with means, and we only know the standard deviation of our sample, not the population. Don't want to dive too much into it in this video, but William Gostin invented the T-models, and he did so because when you work with means, sometimes the only standard deviation you have is that of your sample, not the population. If you do know the standard deviation of your population, then you could actually use a Z-star with your with a confidence interval working with means. Now, just to briefly show you, your calculator is actually where we're going to get your Z-star and T-stars from, and we're going to go to second vars. Now, you can also get these values on the tables, the Z tables and the T tables, if your teacher teaches you how to use those tables. But your calculator gets them very quickly as well. So invert norm is where we're going to get Z stars. And again, remember, it's completely based on your level of confidence. So for example, if I'm asked to be 95% confidence, I could do a couple things. If you have this cool feature of your calculator that shows left center, right? You could type in 0.95, but then go down and select center. And that will give you the Z star that you need for that level of confidence. But most of us, at least, I know I do here, but a lot of people don't have that option. And that means if you don't have that option for the tail, left, center, right, it's automatically set to the left. So this is where we got to think a little bit. If I'm 95% confident in the middle, that means 5% is left out. That 5% is split up due to symmetry, 2.5 at the top, 2.5 at the bottom. So if I type in 0.025 and then leave it on left, and if you don't even have the option for left, center, right, you're automatically set to left. So this is how you would get that Z star. Again, 95% confident in the middle, 2.5% at the left, and this is where we're going to get that Z star. In this case, it'd be 1.96. Now you see that it's negative. That's because we did the left. The top would be positive. And that's exactly why confidence intervals are plus or minus. So it's plus or minus that 1.96. Let's just do one more for practice here. Let's say you want to be 98% confident. We're going to go down, select invert norm. 98% leaves 2% out, 1% at the top, 1% at the bottom, 1% to the left, 1% to the right. So if I'm going to leave it selected as left, I'm going to do that 1% on the left, and my Z star would be 2.326. So you see that when you are more confident, everything else staying the same, your interval will get wider. I'll repeat that one more time because that's a big question on the AP Stats test sometimes. Everything else left the same. If you are more confident, 99, 95, 98, 99, as you get more confident, your interval will get wider. Now, how about invert T to get T stars? We're going to go second vars. We're going to go down here to invert T. Now, invert T does not give you the option for left, center, and right, even if you have one of the new calculators, so it's automatically set to the left or the bottom. So once again, if I want to be 99% confident, that's 1% left out, 0.5% to the left, so 0.005. Now, the only other thing that degrees of freedom are needed here for the T star, because remember, William Gossett found out that there's actually many, many T models, and they all vary based on the degrees of freedom. So this is where you would need to know your sample size, and the formula for a single sample is your sample size minus 1. So let's say you have a sample of 45 people, that'd be 44 degrees of freedom. And we're going to go ahead and paste that in, and that's how we would get our T star for our critical value there. All right, so hopefully that's a quick review, but really, if you think about it, it all comes down to sampling distributions. All confidence intervals are based on a sampling distribution. So let's just say we're looking for the true proportion of teenagers that vape. Somewhere in the center of the sampling distribution is that true value, but we don't know what that is. That's the whole point, is we don't know it. But that's why if we grab a sample, our sample will be somewhere in this model, right? Because a sampling distribution shows all possible p-hats, all possible sample proportions. So maybe this is where our sample falls. And this is the idea that if we grab an interval around our sample, hopefully, like we did in this picture, we caught the truth in our sample or in our interval. Even if we do another example here, maybe my sample ends up being up here on the high end. Once again, when I cast an interval around my sample proportion, I catch the truth. So that's the whole idea of why we're 95% confident, because we say, hey, listen, 95% of samples are near the truth in the center. So we are assuming our sample is one of those 95%. That way, when we built an interval around it, we will capture the truth in it. Now, let's talk about standard error. So here's the cool thing. All of the standard error formulas that you're going to need, let me quickly go back here for a second. Remember, the margin of error is a combination of two things, the critical value, T star, Z star, which we just talked about, and the standard error. All standard error formulas that you could ever need are on the AP Stats formula sheet. So here is the box of formulas working with proportions. So if we're looking for a single population proportion, like what's the proportion of all teenagers that vape, right here is the standard error formula. There it is. Pretty easy formula. Square root of your sample proportion times 1 minus your sample proportion, all divided by your sample size n. If you're looking at the difference between the proportion of kids in California that vape and the proportion of kids in Ohio that vape, here we're looking at the difference between two sample proportions, and right here is going to be your standard error. Pretty cool that all those formulas are there for you. Here is the box on your formula sheet for means. If you're looking for a single population mean, like the mean weight of all bullfrogs, here is your standard error formula. We're going to take the standard deviation of the sample S divided by the square root of our sample size N. If we're looking at the difference, as I mentioned earlier, between the average height of a female police officer and the average height of a male police officer, we're looking at the difference between those two population values. Here is our formula for standard error right here. Pretty easy formula. Just make sure you use the formulas correctly. They're on that formula sheet. And lastly, if you're working with slope, you're trying to find the slope between two values, or between two quantitative variables. Right here is the formula for the standard deviation, or standard error. Now, most of the time, you will actually never ever use this formula, because I'll show you a little bit later on in this video. In your computer output tables for regression models, you are actually given the standard error. You don't even have to worry about calculating it. So although there is a formula for it, I'm going to be honest, in 20 plus years of looking at AP Stats exams, never seen them actually have you use that formula. All right, so let's just talk about the process real quick, because you do have to trust the process. In any problem that asks you to construct a confidence interval, now listen, if it's a multiple choice, you don't have to follow steps, you just find the interval. But if it is an FRQ, you do have to trust the process. So there is a 4-step process. Step 1, name the parameter you're trying to estimate and the procedure. So I'm going to try to find the true proportion of teenagers in Ohio that vape, and I'm going to use a 1 sample Z interval. And then you got to check your conditions. Most of the conditions should sound familiar if you've been working and studying. The sample got to be random to avoid bias. The sample has to come from a random sample. Your sample size must be less than 10% of the population so that we could assume independence in our samples. And finally, the sample size must be big enough. Now, this big enough condition is actually kind of a tricky one, because it all depends what you're looking for. If you're looking for proportions to be big enough, we need 10 or more successes and 10 or more failures in our sample. So if I'm looking at the proportion of kids that vape, I need 10 or more kids that vape in my sample, and I also need 10 or more kids that don't vape. If you're working with means, your sample, well, it can be big enough in a couple different ways. The central limit theorem says if your sample size is 30 or larger, you're big enough, boom, don't have to worry about it. If your sample size is under 30, but the population is known to be normal, then you're already big enough, you don't have to worry about it. And then if you're under 30 and the population is unknown, well, then actually you're still good as long as your sample is, if you actually take a look at the data in your sample, if there's no major outliers, no major skewness, you are still okay to proceed. Now, step 3 is the fun part. This is actually where you just do all the math work to build the interval, as I already talked about. And then step 4 is when you make your conclusion. I'm 95% confident the true proportion of kids that vape is between 10 and 20%, whatever it ends up being. All right, let's just do a couple examples here real quick so you can see how this is going to work. So a sample of 175 Canadian men showed that 8% cannot ride a bike. Create a 95% interval for the population proportion. So obviously I'm going to name it. This is I'm looking for a proportion, like it literally says proportion. So I'm looking for the true proportion of Canadian men that cannot ride a bike. You don't want to have that in step 1. Step 2 is going to be checking those conditions. It needs to be a random sample to assume that we're not going to be biased in any way. So you got to make sure we have that. We need to make sure that the sample size is less than 10% of the population. There's millions of Canadian men, so I'm pretty confident 175 is less than 10% of all of them. And then also we need to make sure very quickly that we have enough in our sample. So remember, we need to have 10 or more successes. So in our sample, we had 175 and 8% of them could not ride a bike. That is 14. Again, as long as it's 10 or more, we're big enough. And then of the 92% that could ride a bike, that number also needs to be more than 10 or more. Now, again, it's pretty obvious it's going to be, but we actually get 161 there. So as long as both of those numbers are 10 or larger, we're good to go. So you guys need to do all that on your own. Like, I'm pretty confident that you could follow those steps pretty easy. Now, let's actually talk about the work here. It's actually so simple. So first, I'm going to start off with my estimate, my point estimate. This is what our samples showed, 8%. But we have to admit that that's just a sample, so we're going to go up and then we're going to go down by what we call the margin of error. Now, the first thing I need is my critical value. I'm going to go to my calculator for that. This is where I'm going to use an invert norm to get my Z star. Anytime you're working with proportions, you could use Z stars. So remember, I'm 95% confident. That's 5% outside, which is 0.025 to the left, 2.5 to the left, 2.5% to the right. I'm going to leave my calculator set as left. That's why, some kids don't have that option, so I always leave it that way. All right, that's going to get me that 1.96. Ignore the negative because actually the negative's already counted for right here with the plus or minus. So 1.96 goes there. Then I'm looking at a single proportion. So I need the formula for the standard error. Quickly go right here. Here it is, right there. Actually, let me circle with a different color here. There is my formula. So giant square root, my p hat times 1 minus my p hat divided by my sample size. So what that's going to look like for me is this. My p hat was 0.08. The opposite is 0.92, all divided by my sample size of 175. Now you're going to grab a calculator and calculate that margin of error. Type it all in at one time. There's no need to do it in parts. 1.96 times the square root of 0.08 times 0.92 divided by 175, and we get 0.040. So 0.08 plus 0.040. So if I subtract, I'm going to get 0.04. If I add, I'm going to get 0.12. There's my confidence interval. So now the final step 4 is I'm 95% confident that the true proportion of all Canadian men that cannot ride a bike is somewhere between 4 and 12%. Pretty simple, pretty easy, not overly complicated. All right, let's do one more here, another example. A sample of 45 parts manufactured during the day shift, so this is 45 parts from the day shift, had a mean weight of 10.6 kilograms and a standard deviation of 1.2 kilograms. Another sample of 50 parts from the night shift had a mean weight of 9.7 kilograms and a standard deviation of 0.8 kilograms. Construct a 98% confidence interval for the population mean difference between the two shifts. So obviously our sample showed a difference. We want to construct a confidence interval for what the true difference between all parts from the night shift and all parts from the day shift could weigh. All right, so the first thing I am going to announce that I'm looking for, what I'm looking for, right? I'm looking for the true population mean difference between the two night shifts, day shifts. Okay, you get that. Check the conditions. Got to be random samples to avoid bias. Both samples have to be less than 10% of the populations they came from to assume independence. And again, we need both samples to be big enough. Well, when you're working with means, as long as the samples are 30 or larger, you're big enough. Central limit theorem says we're good enough. Both samples are 30 or larger. So now let's just get right to the work here. That's my actual favorite part. All right, so if we're looking for a difference, right? Well, the first thing I got to start off with is what was the difference I saw? Well, I saw a difference of 10.6 minus 9.7. I'm assuming you guys most people could probably do that in their head, but overly not too difficult. Grab a calculator if you need to. So I had a sample difference of 0.9. Now I'm going to add, I'm going to subtract. Now I just need to create my margin of error. All right, first thing I need is my T star. So this is when you're working with means, and the only standard deviation you know is that of your sample. You need to get a T star here. So I'm going to go to invert T. All right. So 98%, I believe is what it asks for. Yep, 98%. So at the bottom to the left would be 1%. Now, what's the degrees of freedom when we're working with two samples? Well, there's actually a pretty complicated formula that you don't have to worry about. A couple different teachers might show different ways. Two different things you could do. You could use the smaller of the two degrees of freedom. So I got 44 and 49 degrees of freedom. So the small of the two would be 44. You could also add those together. So you could add 44 and 49 together. Now, those are going to get a little bit different values, and the AP Stats test is okay with that. I recommend using the smaller of the two, to be honest. All right. So I get 2.414 as my T star, my critical value. Next, I'm working with means, and I'm looking at the difference of means. So let me go back to my formula sheet right here, and this is the formula I need right here for the standard error. Again, it's all there for you, just got to know how to use it. So I'm going to start off with a giant square root. I'm going to do day shift first. That's 1.2 squared divided by the 45 parts from the day shift, plus 0.8 squared, that's the standard deviation from the night shift, divided by the sample size of 50. All right, now I'm just going to grab my calculator. Let me move it over here so we can see all the work. And I'm going to calculate my margin of error, 2.414, square root, 1.2 squared, divided by 45, plus 0.8 squared, divided by 50, and I get a margin of error of 0.511. So 0.9 plus or minus 0.511. Now I'm going to grab my calculator one last time, take 0.9, subtract 0.511, take 0.9 and add 0.511, and I get an interval of 0.389 to 1.411. 0.389 to 1.411. So here's, now when you're working with the difference, you want to kind of change your conclusion just a little bit here. So I'm 98% confident that, now hear me out on this, right? I specifically did the day shift minus the night shift, and my interval was entirely positive. So what that tells me is that I'm 98% confident that the day shift will have the weights, the mean weight of products made by the day shift will be anywhere from 0.389 kilograms to 1.411 kilograms more than the night shift. So what I'm concluding, because the entire interval is positive, is that I'm pretty confident here, 98% confident, that the mean for the day shift will be more. Anywhere from 0.389 more to 1.411 more, but it will be more with 98% confidence. You can also flip that around and say that you're 98% confident that the night shift is going to be smaller, less as a mean, 0.389 less to 1.411 less. But again, it will be less. So if we, another big follow-up question anytime you're working with the difference here is, is there a difference? Well, yes, I would say there is a difference because I'm clearly stating with 98% confident that the day shift is going to be more on average than the night shift. Now, if my interval, let's just kind of play the pretend game for a second. If my interval ended up being like negative 0.1 to positive 1.3, just kind of making it up here. Well, that interval actually contains 0, which means there potentially could be no difference between the night shift and day shift, meaning that they're probably just the same. The negative would show that the night shift is actually more. The positive would show that the day shift is more, meaning the night shift could be more, the day shift could be more. There might even be no difference because 0 falls in that interval. So again, just think about the ramifications of that happening if it did. But based on the work that I did for this particular problem, pretty confident the night shift is going to be less than the day shift. All right, hopefully that makes a lot of sense. Now, what else is it that you possibly need to know? Well, there's actually a lot going on with confidence intervals, so I want to take some time to talk about a couple more details that are going to be really important for you to understand, especially when it comes to multiple choice questions. So what else do you need to know? Well, you need to know how to interpret the interval, which is really step 4, but you got to make sure you're very clear on that, so I want to talk about that. Know what the confidence level means. Like when we say 95 or 98% confident, like what the heck does that even mean? How to solve for a sample size with a given margin of error, and also know how to find the point estimate and the sample size from a given interval. So let's kind of look at a couple problems that deal with these topics. These make for great multiple choice questions that often come up on the AP exam. So, interpreting an interval. So here's a quick example. In order to estimate the mean number of hours that high school students at a large high school in Ohio get per night, a 98% confidence interval was constructed, and the interval was from 4.6 to 6.7. So maybe a multiple choice question gives you this and simply says, hey, interpret the interval. This is where we want to make sure that we lead by our level of confidence. We want to start off with our, hey, I'm 98% confidence, and then we want to make sure we have the context of what it is we're looking for. A lot of times, sentences will have a couple different things wrong that make it the wrong choice. So here's the good answer. I'm 98% confident the mean number of hours of sleep for all high school students at this school is between 4.6 and 6.7 hours per night. Keep in mind, oftentimes they'll try to trick you and they'll say, I'm 98% confident that the mean number of hours for the sample of high school students. No. We already know what the sample is. It's the population proportion, or in this case, population mean, that we're actually trying to find. So make sure you choose the one that's talking about looking for the mean of all high school students at this school, not just, a sample. So that should be your step 4, your conclusion. But again, a multiple choice question could simply want you to do that. Here's another one that wants you to interpret the level of confidence. So same problem, they give you the interval, 98% confidence, but the question, multiple choice question says something like, hey, what is meant by 98% confidence? Or which of the following is the correct interpretation of 98% confidence? So keep this in mind. 98% confidence has nothing to do with probability, nothing to do with chance, nothing to do with time. It's all about samples. Our data was collected from one single sample. But there are many, many other samples out there. So the idea of 98% is that if we were to look at all other possible samples, or many, many, many other possible samples of the same sample size from the same population, 98% of those samples would in turn create an interval that contains the true population. So again, some choices might say there's a 98% chance that the truth is in the interval, or there's a 98% probability the truth is in the interval. No, 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 no. It's all about samples. Now, that also means that 2% of samples could create an interval that does not capture the true mean within it. Okay, it is what it is, but I'm not going to be Mr. Pessimistic here. I'm going to be optimistic that my sample is one of the 98% that will have the true mean inside of it. That is why I can't say with 100% confidence that the mean is in my interval. I'm only 98% confidence. But it's a very common AP question, so make sure you really choose carefully and read each choice carefully as well. All right, another task is being able to find the point estimate and the margin of error. So again, same problem here. I have this confidence interval for the mean number of hours that high school students at this high school sleep per night. And maybe a simple multiple choice question is, what was the point estimate? Now remember, the point estimate is what was your sample mean. Well, remember how confidence intervals are created. They start off with a statistic, and you go up and you go down, which means the statistic is dead center in the middle. So to find the sample mean, I just have to find out what value is directly in between 4.6 and 6.7. Now, if you can't do it on your own, just use a calculator. How do you find the middle of two numbers? Add them together. Oh, I didn't add them together. So 6.7 plus 4.6. Sorry, I hit the wrong button there. Add them together. Divide by 2, cut it in half, and boom, there it is. So my sample must have had a mean of 5.65 hours of sleep per night. Now, what about the margin of error? The other value I need is the margin of error, but the margin of error is simply how much you go up and down from that center point. So if I take the top, 6.7, and I subtract the 5.65, or if I take the bottom and subtract, right? Either way, I'm going to get the margin of error of 1.05. So in the middle was my sample mean of 5.65. If I go up my margin of error of 1.05, I get to the 6.7. If I go down, I get to the 4.6. And again, you can actually check that if you want. Again, take the 4.6 minus the 5.65. This is just looking at the bottom half. And I get negative 1.05. So there's my plus or minus my margin of error. So my margin of error here is that plus or minus 1.05. Now let's turn our attention to a second example, this time dealing with proportions. In order to estimate the proportion of customers at a store that use a recent coupon that was available through social media, a 95% confidence interval was created. So owner of a store wants to know, hey, what proportion of customers are using a coupon that we put out there? So they get a sample and they produce this interval from 14 to 18%. So again, I can ask you to interpret it. I'm 95% confident that the proportion of all customers that use this recent coupon available through social media is somewhere between 14 and 18%. I can ask you to explain what 95% confidence means. Well, if we look at many samples, 95% of the samples will create an interval that contains the true population proportion. I'm just hoping that mine is one of them. Now, another thing I could ask you to do is, once again, what is our sample, right? What was our p-hat? What was our margin of error? Well, why am I using p-hat this time? Because this problem deals with proportions, so the statistic that's going to be smack dab in the middle is the sample proportion. Pretty easy, actually. I don't even really need to grab a calculator, but feel free to add those together and divide by 2. But you get a sample proportion of 0.16 right in the middle, and the margin of error is also pretty easy to see. That's the amount I would go up to the 0.18, down to 0.14. That would be a margin of error of 0.02. So a lot of information that I could ask you, or the AP test could ask you, simply from looking at a confidence interval. Now, here is probably, I don't want to say this is one of the harder questions, but this one involves a little bit of work. All right, so finding the sample size. So same problem. In order to estimate the proportion of customers at a store that use a recent coupon, blah, 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 we have this interval of 0.14 to 0.18. What was the size of our sample? Okay, this is a little bit tricky, so bear with me. This is going to involve a little bit of good old algebra work. The formula for margin of error is the back part, right? That is, again, the critical value, in this case, my z star, because I'm working with proportions, times my standard error. The standard error for a single proportion is p-hat times 1 minus p-hat, all divided by the sample size. Now, that is where the sample size lies, right there, and that's what I need to solve for. So I've basically got to fill in the blanks for everything else. So again, I already determined on that previous page that the sample proportion is the 0.16 that's smack dab in the middle. The margin of error is the 0.02 that I go up and down. So I'm just going to substitute that in. The margin of error is 0.02. The p-hat is 0.16 times the opposite. 1 minus that would be 0.84 divided by my sample size. Now the only other value I need is my z-star, which I already addressed in this video a little bit about trying to find that. So I'm going to grab invert norm here. Now some kids will actually start to memorize these numbers, but 95% confident in the middle puts 0.025 to the left, 2.5% to the left. This is going to get me my z-star for 95% confident, 1.96. Now all I have to do is do some fun algebra to solve for n. First thing I'm going to do is divide by the 1.96. Then I'm going to square both sides. When I square both sides, it's going to get rid of the square root. So again, I know I'm showing a couple steps in one here, but I'm assuming you guys are pretty decent at algebra. Now I'm going to multiply the n over to this side, which is going to get rid of the n that's in the denominator. And then I actually have only one more step left to solve for n. I'm going to divide the 0.16 times 0.84 by the 0.02 divided by 1.96 all squared. When I divide, that'll cancel it out, and that'll leave me with just n. So grab a calculator and just start typing 0.16 times 0.84, almost typed that wrong, divided by, and then I need parentheses here, that's the 0.02 divided by 1.96. Close those parentheses and make sure that overall value gets squared. Now I get roughly 1,291 people. Always round up. Again, you're going to be a little bit low or going to kind of miss your margin of error if you round down. So 1,291 people must have been in my sample that created this particular interval. That's a pretty common multiple choice question. I've even seen that on an FRQ before where they want you to use an interval to actually work backwards and solve for your sample size. Now, another type of really good type of problem is one where this is, again, every year this is on the AP exam on a multiple choice at least, determining how big of a sample size you need to create a certain margin of error. So it says a school district wants to determine the proportion of voters that will favor a school levy to help fund the school more money. They wish to create a 95% confidence interval with a margin of error of plus or minus 2%. How big of a sample do they need? So what we know here is we start off by saying, hey, we want a 2% margin of error. So how big of a sample do we need to produce such a margin of error? So once again, I'm going to remind you that we simply need that margin of error formula. That's the entire back part to a confidence interval. So that's going to be my z-star. I'm working with proportions here. It clearly says the proportion of voters. Times the standard error for a single proportion. I'm only looking for one proportion. The proportion of voters are going to favor the school levy. So that's going to be a giant square root p-hat times 1 minus p-hat divided by my sample size. Now let's start filling in what we know. We know the margin of error that we desire is 0.02. You don't necessarily need to worry about the plus or minus. The z-star is based on your level of confidence. We actually just did this in the previous problem. The z-star for 95% confidence is 1.96. Now the big problem is this. I don't know what n, so I'm clearly going to leave n. In fact, that's literally what it says, solve for my sample size. But what is my sample proportion? I haven't even selected the sample yet. I don't even know how many people to select that could even give me my p-hat. So there's two options here. Option number one, we're just going to fill this in with 50-50. 0.50 and the opposite of 0.50 is 0.50. Now, if the problem did tell us maybe something like, hey, last year they did a sample and the proportion was 60%, then you could use that last year value and put a 60-40 there if you wanted. But if they don't give you any indication of what the proportion could even potentially be, you just got to use the 0.5 and 0.5. Actually makes it pretty easy. All right, now I have to solve. So again, just like I did in the previous problem, I'm going to divide by the 1.96. Then I'm going to square both sides completely to get rid of that square root. Then I'm going to multiply the n over to here. That's going to cancel it out from dividing. Then I'm going to divide by the 0.02 divided by 1.96 all squared. That'll cancel this out and leave me with just my sample size. So again, grab a calculator, very similar math to the one I just did, 0.5 times 0.5. You could even make that a 0.25 if you wanted. Divided by, don't forget about these parentheses, you need the margin of error divided by the z-star here, 1.96, and then make sure all of that gets squared, and we get 2,401 people. So the sample size would need to be at the very least 2,401 people in order to produce that margin of error of 2%. Very, very common multiple choice question. All right, The last thing I want to talk about in this video is the last type of confidence interval, and that is a confidence interval for slope. So the idea in this particular problem, if you've been watching some of my other videos, I've actually used this before, but just to give you a quick recap here, in a particular problem, we were looking at a scatter plot, which was looking at the number of rail cars on a train and the fuel consumption of that particular train. And we saw that there's more rail cars, there's more fuel consumption. More rail cars means it's heavier, you need more fuel, you get the idea. And we put a line of best fit through this data, and the slope of that line of best fit is right there. Remember, the column, the very first column is in alphabetical order, A and then B. A is your y-intercept, B is your slope. So B, my slope, is 2.1495. That tells me for every one more rail car that gets added onto this train, we are expecting 2.1495 more units of fuel per mile. Okay, great, but the most important thing is this was just from a sample. One sample. I know it's not written here, but I'm sorry for not writing it. This came from a sample of 20 trains. 20 trains, we looked at the rail cars and the fuel consumption. Okay, but what's the slope for all trains? Not just these 20, all trains. Well, that requires a confidence interval. So once again, remember that generic formula for a confidence interval. Start off with a statistic, something you found from your sample. In this case, that's my slope. I literally want to find a confidence interval for the slope, 2.1495. Then we're going to go up and we're going to go down by the margin of error. The margin of error is that critical value multiplied by the standard error. Now, if you actually go to your formula sheet, you will see that there is a formula for the standard error, but we don't need it. The second column, right next to the A and the B, are the standard errors. And literally right next to your slope is the standard error that you will need, 0.1396. So although there is a formula for it, you will never need it, I promise you, because we have it right here. Don't have to do any work to find it. So the only other thing we need is our T star. Why do we need T instead of Z? Well, because slope comes from quantitative data. Quantitative data has standard deviation. And if you're using the standard deviation from your sample and not the standard deviation from your population, William Gossett reminds us that the T model is better. So I'm going to go ahead and get my invert T here to get my T star. Now I'm 99% confident. So that means there's 0.005. There's that 0.5% to the left. Hopefully you've explained that. Now what about degrees of freedom? Now our traditional degrees of freedom formula is sample size minus 1. But for slope, there are two variables. In this particular case, rail cars and fuel consumption. So the formula for degrees of freedom with slope, something you just have to memorize, is your sample size minus 2. So if I have 18 trains, then my samples, excuse me, I said that backwards. If I had 20 trains in my sample, then I have a degrees of freedom of 18. That's going to get me my T star, 2.878. All right. Now, I've actually seen multiple choice questions where they're leaving the choices looking like this. So they're making sure that you're putting the right slope here, the right standard error here, and the right t-value. But I've also seen them where they actually finish it off and do all the math. So I'm going to go ahead and do that. 2.878 times the 0.1396. Whoop, I put a minus, not a times. I'm so sorry. Terrible mistake. There it is. And I get a margin of error of 0.402. So 2.1495 plus or minus what was it again? 402. And now I'm going to go ahead and actually add that and subtract that. And again, the idea here is this was the slope, 2.195, 2.1495. Try to type with this thing is not always easy. This is the slope from a sample, but that doesn't mean it's equal to the slope of the population. And that's exactly what I'm trying to estimate right now with this confidence interval. All right, so I get anywhere from I'll just round that to 1.75 and 2.55, 1.75, 2.55. So here's what I know based on looking at this interval, is that there is going to be a positive slope. There is, right? There is going to be a positive slope. Positive simply means if I add rail cars to trains, I'm going to increase the fuel consumption. But how much am I going to increase that fuel consumption? Well, that is what I don't know for sure. It's anywhere from 1.75 units per mile to 2.55 units per mile. But I know I'm going to have to increase my fuel consumption when I add train cars on. It's just how much do I need in the population is not precise. The 2.1495 was simply from this one sample, but the population slope, again, anywhere from 1.75 to 2.55 with 99% confidence. So I very rarely, every now and then, this has been an FRQ, but mostly this is saved for a very simple multiple choice question. So just be careful that you're using the right number here and here. And again, you're literally getting those right from the table. The only thing you got to be careful of is getting the proper T star. So make sure it's your sample size minus 2 for the degrees of freedom, because that could potentially mess you up. All right, so that's it for this video. I hope it makes a lot of sense, and I hope just kind of going over the idea and the concepts and all the little different intricacies of confidence intervals will help you perform really, really well on the AP test. Best of luck to you. Don't forget to like the video. Hope you enjoyed it.